Hello everyone, my name is Yongtae Kim. I'm undergrad student at KAIST in South Korea, and today I'll be presenting our work on cortical visual prosthesis. The title is Differentiable Joint Optimization of Implant Placement and Electrode Selection for Cortical Visual Prosthesis across diverse target stimuli. We call this the PhosInv model. Let's start it. I'll start with the clinical background and the problem we're solving, then walk through our method, our results, and finally what these findings mean for clinical translation. And this is the main figure. Let's begin with the basic idea of the cortical visual prosthesis. For people who are blind because of the damage to the retina or the optic nerve, retinal implants and optogenetic therapies don't apply. A cortical prosthesis bypasses that damaged pathway entirely. It places electrode arrays directly into the primary visual cortex, V1, and converts camera images into patterns of electrical stimulation. Each stimulated electrode evokes a small spot of light that calls a PhosInv. By combining many PhosInvs in space, patients can perceive shapes, contours, and motion. Clinical trials are already underway, but the functional vision these devices provide today is still severely limited. So, cortical prosthetics are the promising but unfinished technology for restoring vision. A core reason for the limitation is that V1 is not a uniform screen. The cortex devotes a disproportionately large area to foveal central vision. This is the cortical magnification factor. So if you place electrodes on the uniform grid, the foveal electrode produces crowded, overlapping PhosInvs, while the peripheral electrodes produce coarse, oversized percepts. A uniform grid is simply the wrong tool for V1. On top of that, retinotopic organizations varies substantially from person to person. So a generic average brain placement will systematically misrepresent the PhosInv layout for any specific patients. The conclusion is the implant placement has to be optimized per subject. The most relevant prior work here is Van Hoof and colleagues from 2025. They use Bayesian optimization to search over the insertion trajectory of the array, and they show that subject-specific placement clearly beats average brain solutions. That's an important result, but their approach was tuned independently for each individual target stimulus, and that raises three problems. First, clinical reliability. A physically implanted array cannot be repositioned between stimuli, so optimizing a different placement for every image is not something you can actually deploy. Second, selectivity. They activated all of 1,000 electrodes indiscriminately, which throws away the benefit of choosing what electrodes to fire. And third, speed. Their search takes about 436 seconds per stimulus. That is completely incompatible with real-time prosthetic vision. So, per stimulus implant optimization, while a useful upper bound, is clinically infeasible for a real device. That is the gap we set out to close. This is the architecture of the solution, the PhosInv model. The input is a square-shaped target PhosInv map, the pattern we want the patient to perceive. That map goes into the CNN encoder, which feeds two branches. The first branch is shared across all stimuli. It's a single learnable vector of 4 implant parameters, 2 insertion angles, an offset, and a shank length. This is fixed once after training as a real implant would be. And the second branch is a per stimulus. An electrode head maps the latent representation to 1,000 doses, and a sigmoid turns those into the active electrode mask, chosen freshly for each target. Crucially, a differentiable simulator connects the both branches to the loss, so gradients flow end to end through the whole pipeline. The result is that PhosInv predicts both the electrode placements and the electrode's activations in the single forward pass. To train the end-to-end, we needed the PhosInv simulator itself to be differentiable, and the original one was not. We made 3 modifications. First, the surface distance lookup table. The original used a non-differentiable ray surface intersections when we replaced it with the pre-computed grid and bilinear interpolation with a mean error of only 0.03 millimeters. Second, soft receptive field matching. Instead of discrete nearest voxel lookup, we use a Gaussian weighted average over V1 voxels. And third, electrode relaxation. During training, we replaced the hard binary mask with continuous sigmoid weights and inference with threshold at 0.5. Together, these three changes make the simulator fully differentiable. For data, we used the Human Connectome Project 7 Tesla retinotopy dataset. We processed 179 subjects and selected 3 as our benchmark subjects. For each subject, we trained 1 model per hemisphere, giving 6 subject hemisphere models in total. Each model was trained on roughly 100,000 PhosInv maps derived from MNIST letter balanced characters. The training object is a composite loss combining a soft dice coefficient and a yield and a Hellinger distance. Also, gradients propagate through this simulator to both the encoder and the shared implant parameters. Our benchmark has 30 targets, designed to test 2 very different regimes. 15 are in-distribution letter targets from MNIST, split into the reconstruction difficulty tiers, 5 each. The other 15 are out-of-distribution synthetic targets the model never saw in training, 5 arcs, 5 single blobs, and 5 multi-blobs. And all targets are square backgrounded with a circle right hemifield mask. This design deliberately gives each method both flappable and unflappable ground, rather than collapsing everything into one biased number. We evaluate 9 methods under 2 clinically motivated conditions. The first condition is per target. This is the clinically infeasible upper bound. It includes Bayesian optimization, which fires all electrodes, and overlap, which adds centroid-based electrode selection on top of the same placement. The second condition is generalized, which respects the real clinical constraint of the fixed placement. This is where PhosInv lives, a shared placement with learned per stimulus electrode selection. We also include 2 frozen reference baselines, BO generalized and overlap generalized, which takes the R3 solution and apply it identically to every target. Finally, we have some ablations that share PhosInv placement, all on and 3 K-matched heuristics, random, intensity, and center. In total, 9 methods, 30 targets, 6 subject hemispheres, giving 180 observations per method. Here are the headline results. PhosInv is about 5,380 times faster than per target Bayesian optimization. That's 0.081 seconds per stimulus, compared with 435 seconds. It also activates about 10 times fewer electrodes, roughly 104, versus the full 1000 used by BO and all-on. That directly reduced the electrical charge delivered to the tissue. And despite the fixed placement constraints, PhosInv achieves the lowest loss amount of the generalized method, so we get speed, electrode economy, and quality at the same time. Let's isolate where the quality comes from. These 5 methods are shared the identical implant placement, so placement held constraints on only electrode selection varies. Compared with all on in distribution targets, PhosInv drops the loss from 2.437 to 1.795. That's a reduction of 0.642, highly significant, so learned electrode selection genuinely contributes. Now look at the 3 heuristics that activate the same small number of electrodes, 104 each. Random, intensity, and center are all worse than all on, even though they fire far fewer electrodes. That tells us sparsity alone is not the point. You need a learned selection strategy, and the CNN is doing real work here. The next question is the most important one. Does the clinical constraints cause us performance? PhosInv under the generalized constraints is statistically indistinguishable from part-target overlap with a p-value of 0.836, and it is not significantly different from BO generalized either, so the generalized constraints on aggregate cause essentially no performance. There is a key quality difference behind the tie. BO generalized applies one fixed arc-tree map to every target. PhosInv adapts its electrode selection to each stimulus. We'll see in a moment that this difference matters a lot when you break results down by target type. By constraint, overlap generalized collapsed from about 2.02 up to 2.56 because a sparse arc-tree map simply fails on non-arc targets. The takeaway is that PhosInv meets the clinical reality of the non-repositionable array without paying a performance penalty. Breaking the results down by target type reveals the structure of the trade-off. On the in-distribution best and mid-tier, PhosInv actually beats per-target Bayesian optimization. A single-pass amortized model outperforms a 150 evaluation search. On the worst tier, the hardest letters, BO recovers, because those targets push the limits of the single shared placement. On out-of-distribution arcs, PhosInv is at its weakest. Arcs need large contiguous fields with the simple absence for the letter training distribution. But on blobs targets, the gap narrows again, because local Gaussian blobs share structure with individual letters postfins, so performance tracks how close a target is to what the model was trained on. If we plot reconstruction quality against inference time, three non-overlapping clusters appear. The slow cluster, around 435 seconds, is the per-stimulus search method. The frozen reference baseline cease at the same time, but that's a one-time artery cost, not a per-stimulus burden. The fast cluster, around 0.025 seconds, is a simple baselines. They match speed, but their quality is clearly inferior. PhosInv sits on its own at 0.081 seconds, roughly 12 Hz. It's the only method that both real-time compatible and competitive in quality. Finally, looking at the predictive maps themselves makes the failure most visible. BO fires every electrode, so it produces a luminous haze that washes out fine structures. The heuristics even fail is their own way, random scatter or localization to the single bright pixels or rigid clusters at the array center. PhosInv produced the most legible reconstruction in distribution metals. You can read the vertical strokes of an I or its open curve of a G. On arcs, as expected, it concentrates in the central cluster rather than filling the full sector. So why does a generalist model beat a per-target search on familiar targets? At first, this seems backward. The method with more degrees of freedom, per-target BO, performs worse. The explanation is about the search problem. Bayesian optimization explores a four-dimensional placement space with only 150 evaluations, and the loss function does not explicitly encode things like Strode topology or spatial sparsity in letters postfix. PhosInv, by contrast, distills about 100,000 training examples into a single forward pass. It learns activation strategies that are effectively invisible to a budget-limited search. And when we decompose the two levers, learned electrode selection contributes substantially more to reconstruction quality than per-target placements does. That points future work towards richer selection strategies. The arc weakness deserves a clear interpretation. Arc target requires large contiguous hemi-filled fields. These are structurally very different from amylase letters in sparsity, in shape, and in spatial distribution. The gap narrows on blobs precisely because blobs share local Gaussian structure with letter phosphines. So the degradation scales with structural distance from the training distribution, not with some category boundaries. And that points to the simple fix. Add arcs and blobs to the trainer corpus, and the gap should close without any change to the architecture. The out-of-distribution weakness reflects training coverage, not a fundamental limit of the approach. So, what does this mean for clinical translation? On viability, PhosInv runs at about 12 Hz, which is real-time compatible, and it uses 104 active electrodes instead of 1000, cutting the per cycle charge delivery rough tenfold. The main remaining barrier is the input. Today, the model needs 7 Tesla fMRI retinotopic maps, which blind patients cannot produce through visual stimulation. Replacing that with a structural MRI-based retinotopic prediction in the style of Ribeiro and colleagues would extend the framework to exactly the patient population we care about. I also add candid about limits. All our metrics are simulation-based, so the link to actual perceived quality is unverified. We use 3 subjects and 30 targets, so anatomical diversity is limited. And we fixed the stimulation amplitude, whereas a deployed device would need per electrode threshold adaptation. To summarize, we reformulated prosthesis optimization as a generalization problem. Instead of solving for the best implant per target, we learned one shared configuration across a large target distribution, and we adapt only the electrode activation per stimulus. The generalized model matched per target Bayesian optimization while running thousands of times faster and using 10 times fewer electrodes. Our observation showed that learned electrode selection is the dominant lever, so future work should prioritize richer selection strategies. The out-of-distribution gap is the coverage problem, fixable by expanding the training corpus, and the clearest path to the clinic is replacing 7 Tesla fMRI with structural MRI retinotopic prediction. Taken together, PhosInv defines a clinically tractable framework for cortical prosthetic stimulation. Thank you for listening, and I'd like to thank my co-author Yeon Seo and Professor Seung-woo Lee and Dae Kim for their guidance and support throughout this work. If you have any questions or feedback, feel free to email me at youtube@yongtae.kim. Lastly, this paper is still under review, so some details might change upon publication. Bye bye.